So first one, we've got a moon orbiting a planet in a circular path. We've got the orbital radius, we've got the mass of the moon and the mass of the planet, and all our answers, these are the things allowed in our answers. First, we want to derive an equation for the velocity of the moon in its orbit. So I started with my free body diagram. This is my planet, and then this is my moon, and it's going around in a circle. The free body diagram would be the forces acting on the moon. The only force acting on the moon is the force of gravity. And then because the moon is moving in a circle, that force of gravity is what's providing my centripetal force, the force that makes it go in a circle. So then centripetal force is just mv squared over r. The centripetal force is the centripetal force of the moon because it's going in a circle, so I'm going to call that mass of the moon. And that's equal to the gravitational force. Now normally gravitational force we just use mg, but it's not like I know the g, the gravitational or the acceleration due to gravity at this point above this planet. So we're just going to use g m1 m2 over r squared. And m1 and m2 would be mass of the moon and mass of the planet. And we are looking for the velocity, so I'm looking for the, again, velocity of the moon. So the mass of the moon cancels out. 1r cancels out, and then now I just take the square root. Velocity is the square root of g mp over r, and that's my answer. We could not just jump to this. I know a lot of you had this memorized. That's great because multiple choice you need it memorized, but for free response, a memorized equation isn't going to work. You got to start with like things that are given. B, derive an equation for the acceleration of the moon. So two ways I can do it. I did centripetal acceleration because it's moving in a circle, and that helps me find the acceleration as it moves in a circle. That's just v squared over r. Ooh, this is supposed to be a capital R, I'm pretty sure. Yeah. So then v squared over r, and now I plug in for v. So square root of g mp over r squared over r. Squaring the square root cancels out. And then I have g mp over r divided by r. This is different than r over r, which cancels out. I have something over r divided by r again, which is dividing by 2 r's, which is dividing by r squared, which is AC, so that is my answer. You also could have thought about it as the little g, which is fg over m, right? The acceleration of the moon would be the force of gravity of the moon divided by the mass of the moon. Force of gravity of the moon would be this, mp over r squared over mass of the moon, and the mass of the moon would cancel, in which case I'm left with the same thing. The reason I could use this is because the acceleration of it as it moves in a circle is just the acceleration due to gravity, so the only force is gravity, but either way works. C, getting the period. Remember, period is the time specifically for one rotation, so the time it takes to go around one revolution, or once. I know that the velocity as it goes around is this. I know it's going at a constant velocity as it moves, so I'm going to use v equals d over t. I'm going to get t by itself, so t is d over v. And then the distance traveled is, right, we just went in a circle. The distance of a full circle is just a circumference, which is on my equation sheet is 2 pi r. So distance traveled would just be the circumference, 2 pi r, and then the velocity is what we just did, g mp over r, so then that is my answer. And I've left it in the things that I'm allowed, nothing that I'm not allowed. Second moon, 10 times the mass of the first moon, orbits the planet at the same altitude. So I've got my moon, and I've got a second moon, 10 times the mass of my moon. And how does this guy's acceleration compare to before? Well, we look at our acceleration equation. The acceleration is g mp over r squared. The mass of the moon doesn't matter at all, so it's the same acceleration because the acceleration has no dependence on the moon mass. Now we're talking about same situation, but how does the velocity compare? So we look at our velocity, our orbital velocity equation, and again, mass of the moon is not in there, so it doesn't matter because velocity does not depend on the mass of the moon. If I had said a greater mass of the planet, then absolutely your velocity would have to be faster, but I increased the mass of this guy, which is not the same thing. If the moon was placed in a lower circular orbit, so what I read this as is smaller r. So if I have a smaller r, what would happen to my period? So if you look at period, oh, I did this again. Okay, now they're good. If you look at your period, you've got 2 pi r over this velocity. 2 pi r, I have r on top. Now you might be saying, well, I have an r on top, but I also have an r on bottom. Technically, you're dividing by a fraction here, which is the same as multiplying by the reciprocal. That's the same as 2 pi r root r g mp like this, which is actually just another on top. Even if it was on like the bottom right here, r over root r, the top r would win because it's a higher power. So it is a direct relationship with r. So if I have a smaller r, that is going to be a smaller period. So your explanation could just be as r decreases, then t decreases, because r and t are a direct relationship, or directly related. Perfect. We've got our popular amusement park ride, a large cylinder set in rotation. The floor drops away, leaving the riders suspended against the wall in a vertical position as shown. The radius is r and the velocity it spins at is v. So at first you're standing on the floor, right? That is providing a normal force up, and then the floor goes away. So when it's just suspended there, do it off to the side. We've got, of course, force of gravity, your mg, and I'm not like zoomed out in outer space. This is like a ride on Earth, so the force of gravity would just be mg. I've got the friction force holding me up, because there's definitely not a normal force holding me down, or holding me up anymore. There's no surface pushing up. It's just the friction force keeping me from falling. And then I, of course, have to have some force pointing to the center, because it's moving in a circle. You have to have some force providing the centripetal force to keep it going in a circle, in which case, in this case, it is the wall pushing, so that is the normal force. And these check out because friction has to be parallel to the surface, and then normal has to be perpendicular to the surface, so they check out. Now the equations you can write, so it says that the rider is suspended, so they're not falling, they're also not accelerating up, so these two are balanced up and down. Your Fn is acting as your centripetal force, the thing that's making it go in a circle. Now I can replace F of friction with mu Fn. Or I can replace, not Fn, but I can replace centripetal with mv squared over r. I moved this one over. You can also divide here and substitute, it doesn't matter. So mu mv squared over r equals mg. I'm trying to get mu by itself, so I'm going to multiply the r up. I'm going to divide the m over. It crosses off, and then divide the v squared over. So the mu is g r over v squared, and that is my coefficient of friction. And I'm allowed to have r, v, and physical constants. And I can use little g because if we're on Earth, then my little g, I know. If the cylinder were to rotate faster, would the rider need a smaller or greater coefficient of friction? So rotate faster is talking about your velocity. Faster would be a greater velocity. So as v increases, mu should decrease. They should do the opposite thing, because mu and v are indirectly related, or have an indirect relationship. If the radius were to decrease, so as r decreases, then mu would decrease, because mu and r have a direct relationship. Terrible handwriting, but you can hear my voice. It's okay. So then your answer here, I didn't actually answer it. So you would need a smaller coefficient, because, and then same here, smaller coefficient, because as v increases, mu decreases, because they're indirect or directly related. Right here, we've got a ball of mass m attached to a string of length r and negligible mass. It's moving in a clockwise vertical circle, so vertical meaning like up and down, not on like the surface, but up and down in the air, at a constant speed. When the ball is at point P, the string is horizontal. point Q is the bottom, point Z is the top, air resistance is negligible. Here we want to label and draw the forces exerted on the ball at each point. So at point P, so this is a vertical circle, which means that you do have gravity pulling it down. So this right here is just going to be mg. And then at this point, the string would be pulling it in to the right. So that would be my tension force. At point Q, of course, I still have mg pointing down. Here, the tension force is going to be pulling it up, and I know the tension force is greater right here because it's going to have a centripetal force in the center to keep going in a circle. At which point of these four would the tension be the greatest? So what I did is I drew, we already have most of our free body diagrams, but I wrote my equation for each. So here, Fc equals tension. Here, Fc equals tension minus mg, and I also checked at point Z. Point Z has mg and tension like this, so Fc equals T plus mg. We're trying to look at tension, so I'm going to rearrange. That's Fc plus mg equals tension, and Fc minus mg equals tension. So these are my three tensions. Oops. I'm not going to check M because M is going to be at an angle. I wouldn't be able to find like the exact angles to the exact component, so I'll just look at these three. Where tension is the greatest, so you know that mg is going to be the same, right? Your mass has not changed. The acceleration due to gravity is not going to change at the top or the bottom of the circle, so mg is the same for both. The centripetal force, well, centripetal force is mv squared over r. M hasn't changed, the radius of the circle is not changing, so let's think about our V. Well, it says it's going at a constant speed, so all of these things are staying the same, which means that Fc is going to be the same at all points. So, if I have some Fc, right here my tension is equal to that. Right here my tension is equal to that plus mg. Right here my tension is equal to that minus mg. So where it is the greatest is for sure going to be point Q. What did I write here? So this helps you explain it a lot. So at point Q, your tension is equal to Fc plus mg. Since V is constant, Fc is the same at all points. So tension is greatest where Fc is the tension and the weight. So the same Fc plus the weight is going to be greater than just the Fc, or Fc minus mg. Where your tension would be the least would be right here when you have Fc minus mg, and that was at the top, so point Z. And basically the same reasoning here. At point Z, tension is Fc minus mg. You don't need to restate this, right, because you've already said that Fc is the same. So T is the least where tension is Fc minus the mg, right, without the mg. Another way, if you didn't use the equation, you could have said here tension has to overcome the force of gravity in order to maintain the same centripetal force, whereas here you have gravity with a smaller tension maintaining that same centripetal force. But I think this is always clear because you're like, I'm adding here, I'm taking away, which is why it's bigger and smaller. If the ball was hurled at the same speed but at a larger radius, would the new tension at point Q be more or less than before? So we've already said tension at point Q, that the tension is Fc plus mg. Now if you just look at this, you're like, it has no dependence on r. Careful, because centripetal force is mv squared over r, which definitely has a dependence on r. So what I would say is, since your mass and velocity are constant, but with a larger radius, your Fc will be less. And I would maybe just put because Fc is mv squared over r. So that's showing like, okay, a larger radius would be less Fc. So since this Fc will be less, at point Q, tension is Fc plus mg. So less centripetal force with the same mg will be less tension. So again, using your equations, you're saying, okay, T is Fc plus mg. This is the same, but now I'm adding it to a smaller Fc, and I know Fc is smaller because Fc is mv squared over r, so a larger radius would mean less centripetal force. Last one, block of mass m is on a turntable, distance d from the center. The block turns with tangential velocity v. Draw a free body diagram. So this is on a surface. We are not in outer space, like talking about different planets. So I just have mg pointing down, and then the surface is holding it up. So that's going to be a normal force. These two are going to be balanced because it's not accelerating up or down. But it is turning in a circle, which means I do have a force pointing to the center. We never put Fc as a force, right? A force can serve as a centripetal force, the way like a force can provide my net force, but net force is not a force on its own. It has to come from something else. In this case, the reason that it continues is because there's friction holding it in place. If there wasn't friction, if this was like ice all of a sudden, it would slip off. So this is my force of friction. Now I can say these two are balanced, Fn equals mg, and I can say that my Ff is just acting as my centripetal force. So then, force of friction is mu Fn, Fc is mv squared over r, except it called me a distance d, so that is acting as my radius. Fn is just mg, so this is mv squared over d equals mu mg. Cancels, I'm looking for mu, so just divide g over, so then mu is v squared over dg. If the mass of the block were increased, would we need a greater or lower coefficient? This would be the same coefficient needed, because mu has no dependence on m. If the block were placed closer to the center, would we need a greater or lesser coefficient? So closer to the center means less distance. Less distance is going to mean a greater coefficient. So greater coefficient because as d decreases, mu increases because d and mu are indirectly related. Like and subscribe.